Students, we'll start the lecture number 16 today. So that means I have 4 more lectures to deliver. After that, Professor Pratik Ray from IIT Ropar will deliver his lectures. And we have been discussing in the last few lectures about machine learning methodologies. Machine learning is a very important portion of any data science course, especially for material informatics. As you know, machine learning techniques allow you to model different kinds of phenomena in material science. So, as a part of this series on machine modeling models and applications, I have discussed about several machine learning models or types of models, linear models, mostly regression, and then we talked about SVM, support vector machine, decision tree or DT. Previously, I discussed about Bayesian concepts. In the last 2 lectures, I discussed about neural networks. Today, I am going to talk about more about clustering. So that will be the main portion of this third part of this course. So before we go into clustering, today we are going to discuss much detail about that. Let me first take few moments for whatever we have learned in the last lecture. So in last lecture, we talked about neural network and artificial neural network. And neural network, artificial neural networks, sometimes both are used simultaneously, but they are not same. Artificial neural network is more widely known, which is called as ANN, and that's widely used for mostly machine learning as well as deep learning. So I am only talking about very brief about this technique, how this technique is developed, what are the ways this technique can be used. If you want to really know how this technique can be used in deep learning methodologies, please look into my course on artificial intelligence and machine learning in materials engineering. So I have discussed many techniques which are based on artificial neural network in that course. So artificial neural network is basically an imitation of human neuron. How does a human neuron or biological neuron works? It is very important that you understand it. Any neuron has 4 important parts. First one is called dendrites, which collect the information, that means which collect the values of the variables, what you can say, and this information is subsequently processed in the cell nucleus. Soma is the cell body, and nucleus is the center of that, and this nucleus processes the information obtained by dendrites. Subsequently, the processing information is transferred to the axon, and axon goes to the next neuron via synaptic synapses. So that's something which is very simple picture of a biological neuron. Now, can you mimic it? Very easily, we can mimic that. That's what is shown at the bottom. You can see here you have input variables as x0, x1, xn, and you have weights w0, w1 to wn. So what do you do with weights? Weights are basically used to make sure that certain values, certain variables have more impact on the output than the others. If it's not so, we can put the same values on each of the weights. Otherwise, values of the weights can be varied and also optimized. So we multiply each of these weights with the variables x values and get w0 x0, w1 x1 to wn xn. Subsequently, sum it up everything. Why do you sum it up? Then we get the full picture of all the variables, how they are affecting, right? And then on this sum, we apply what is known as an activation function. These functions convert this summation into an output. Let me also tell you that ANN is a parallel processing system, just like a biological neuron. The input of the neuron is fed, the output of a neuron is fed to the input of the next neuron, and this process continues or basically goes on. So that means you have a different layers of these networks. So in a nutshell, what we can do? We can tell that these are my inputs x1, x2 to xm. We have weights w1, w2, w3. In the last slide there are w0, but it's okay, you can put that. Sum it over, process which is using a transfer function or activation function to get an output, right? That is what is this this is what the signal is not passed down to the next neuron verbatim. It is basically processed and then only transferred to the next neuron. So, but in order to solve complex problems which we human have to handle, we need to modify this little bit. That is what is done in multi-layer perceptrons. So, when you have the ability to detect something very nicely, it is a pattern which can be detected very easily, because we can process informations in a very high level and also at high accuracy. So, therefore, can we build such a kind of aspects in a ANN? Well, yes, it can be built. So, artificial neural network are basically computation systems that intend to imitate human learning capabilities by a complex architecture, and that can actually resemble human nervous systems. So, what is a perceptron actually? This perceptron or multi-layer perceptron is a tool to do that. What is a perceptron? It is basically a simple binary classification algorithm. It was discovered by Frank Rosenblatt from US, and this here we have a binary classification. I talked about classification a lot. So, that means what? You have a 0 and 1 as an output. So, perceptron is modeled using a concept known as a essentially a unit of the human brain, that is what neuron is. And it is a very simple learning machine which can take few inputs, multiply by outputs to signify the importance of the inputs, and generate an output which is basically 0 and 1, correct. So, therefore, any neural network can in principle answer any question using enough training data, computational power, and complex networking systems. So, at this point it is very important to tell you difference between this multi-layered perceptron vis-a-vis neural network. In a neural network, decision functions are not continuous basically. Decision functions are rather what? That continuous function, but in MLP decision functions are basically step function, and output is always a binary 0 and 1. And because the neural networks most probably evolved from MLPs, activation functions can be used which results in real value inputs, which can vary between 0 and 1 or -1 to 1. So, how does this MLP work? We talked about little bit. Basically, we have inputs, then we get a lot of hidden layers, as I told you, right. And these inputs are basically multiplied by weights, sum it over, and then output of each of these inputs layers are transferred to the next layer, hidden layer, and finally you get a final output. Let me discuss in a detailed manner. So, multi-layer perceptron is basically a network which is formed by teaming up of perceptrons with many layers, so that it can handle complex problems. Each perceptron in the first layer, which is called an input layer, takes the input values, sends the output to the next perceptron, that is what is called second layer, or we here marked as a hidden layer, you can see here hidden layer, and all the perceptron in the second layer then calculates and then sends the output to the next layer, which is known as a output layer. Actually speaking, you can place many such hidden layers, as many as hundreds or thousands also. So, when 3-layer MLP use, it is called a non-deep or shallow neural network, but when you have more than 4 layers or 4 or more layers, we call it deep neural network. Remember this. That is a part of deep learning technique. That is why it is called a deep neural network. So, in a nutshell, I can put it together like that way, because since you will be using this MLPs quite a lot in your solving the material informatics problems. So, as you see here, we have 1 x1 x and n values, input values, and we have weights w0, w1, wn. So, we multiply each of these, sum it over, and apply step functions. That is what is known as a activation functions. I shown you something like this, okay, in the board in the last lecture also. So, step 1 basically takes the weights and multiply them with inputs with the weights, okay. But this weights have to be optimized, or they needs to be fine tuned. How do you do that? We do it by using a technique called a back propagation, that we will discuss subsequent slide. We many cases add bias. That means we have so what is known as a W. So, you can write it known as a W0, plus W1 x1 plus W2 x2, right. So, we always add some bias, okay, B0. Why do you add a bias? Because the values of these variables x1, x2, x3, xn can have errors, and in the weights also we are using needs to be fine tuned. Take care of that, we always put a bias. This is a technical step basically that makes it possible to move the activation curve up and down to the left or right on the number curves, and it is possible to actually make these biases also optimized. So, what the activation function does is fits the thumb through the activation function. One of the activation function I talked about is the sigmoid function. It looks like this, 1 divided by 1 plus exponential to the power z. Okay. So, that is the function we use extensively, that is known as a sigmoid function. So, this z which is you are getting as a sum it over is passed through the activation functions. So, there are few activation functions I have shown you, like the one which I am discussing here is what? The one which is discussing where is this sigmoid function you can see here. Then you can have hyperbolic tangent, you can have rectifier, linear unit or RLU. You can also have linear function simply, or you can have perhaps signal sign change also called signum function. You can use unit step always, right. So, these are the graphs for that. So, then finally, you get an output. So, one of the ways of optimizing weights and the biases basically by using either back propagation, hyperparameter tuning or advanced structures, out of which I told you I will talk about 2, back propagation, hyperparameter tuning. Today I am going to discuss what back propagation techniques which I told you is nothing but a backward pass, right, which helps you to tune the inputs weights of the inputs. It is an algorithm commonly used to train many neural networks. It basically an iterative technique which attempts to minimize the loss or the difference between correct output or actual output with the predicted output. That is what is called loss, right. And in neural networks we have a loss functions. I can tell you that what is the loss functions. Let me just see somewhere down the line. I wrote about the loss function, yeah, correct. Where is the law? Yeah. So, I can go back to the board and show you that. So, loss function in neural network ANN looks like this. Half of do you understand that? So, this is what is your target or actual values, and this is what is your predicted values. So, you have taken difference of that and then mod square, sum it over from all the layers, okay. That is what is done. So, many people call it. So, x here is what? xn rather, these are inputs, w's are weights. I have intentionally did not put the biases here, okay. So, total error we can write down is nothing but error in each step, that is what we can write EW. Okay. So, this is the error which is minimized for back propagation. Let us be clear about it. Okay, that's the error which is minimized for this. And so basically it's the iterative technique. It goes and back and forth. It changes the W's, calculate the output, and again find out what is the difference between the actual value and the predicted output. Okay, so it's not very complex technique, but it's good. So that's what it says. Inputs are loaded. They are passed through a network of neurons. Network provides output for each and again, with a certain given values of the initial weights, and then you can change the weights, go back and find out the values again, compare it. So I can always talk about this as like a football match. In a football match, and you can clearly see the player is moving like this. Instead of scoring directly, he is sending this pass to the next player, and then he moves here and score the goal, right. So that's what is called a back propagation. You simply put it the back or send it back to find the networks. So so back propagation algorithm allows you to perform always back passes, and that makes you to tune these weights, right. And it's really activated iterative process. Idea is to optimize the loss functions or minimize the loss functions rather not optimize, and each time we are going backward, basically weights are optimized to reduce the weight as much as possible. So this is in detail aspect of the sigmoid function. You can see here Fn is equal to 1 by 1 plus exponential e minus 1. This is how it looks like. Linear function will look like this. You can always draw a line. This is your x, this is your y, right. Similarly, this is your y, this is your x, or rather this is your what? This is Fn, right. Better to write Fn. Okay. There are different types of network one can use. One can use single layer networks or multiple input networks. Okay. You can use recurrent network also, which can go and back and forth. That is also possible. Like it can give feedback. That is what is called recurrent network. You can see here output is sent back as a feedback loop. That is called recurrent network. Well, let us move on and talk about a little bit of clustering, so that we can understand something. I told you clustering is what? Clustering nothing but the task of dividing the data into meaningful groups, and based on what? Based on certain kind of a information of the data. So, we are basically dividing our data into meaningful groups based on some information of the data, right. So, this is some people call it task of grouping data based on that similarity. That is what I wrote here in the slide also. This method is defined under unsupervised learning. That means you need only one set of values of inputs or output, right. As you know, we talked about it, you have x and y, right. So, if you have both the values known, then we call it supervised learning. If one of these values are known to you and you want to model, it is called unsupervised learning. And we can actually gain insights from the unlabeled data points. This is what is called label, right, in machine learning. X is called inputs. So, that means you have x only available, y data are not available, and that is why it can be useful technique in case of clustering. Clustering aims to form homogeneous groups from heterogeneous data. It evaluates similarity based on certain metrics. It can be Euclidean distance, some other distance like Manhattan distance or cosine similarity, and they group these points into with highest similarity scored together. That is the in a nutshell. You could see the data points are like this. Immediately you can understand there are 3 different clusters possible. There can be many more clusters possible, but at least visually looks like you can have 3 different clusters possible. So, this is nothing but a task of dividing data into meaningful groups based on informations, similarity like that. How do you do it? There are 3 different types of models. One is called a connectivity model, what is known as a k-means algorithm, which we will talk in detail. In fact, we will also discuss about some mathematics of that. Then you have a connectivity models, which are nothing but a hierarchical clusterings. And finally, you can have density models, which are basically based on what? Based on spatial clustering kind of things like density or spatial clustering. So, one of these called DV scan, right, DV scan. So, let us talk about that, but before that let me also tell you, you can also have flat algorithms or hierarchical algorithms. Flat algorithms usually start with a random partition. There is no initial starting point. It can start with random partitioning and it is iteratively done. K-means is one such technique which we will discuss, but you can also have hierarchical algorithms which are nothing but a hierarchy related. It can be either bottom up agglomerate, you can start with a very go bottom rock bottom and start putting agglomerating and develop a algorithm, or you can have a top down which is divisive. You can divide, start breaking down into pieces. So, otherwise you can also have hard and soft clustering. In hard clustering, each data point belong to a particular cluster only completely, right. Otherwise it can't, okay, that is what it is. For example, let us say there are 4 data points and we have to cluster them into 2 clusters. So, each data points will either belong to cluster 1 or cluster 2. Nobody will belong to both the clusters. That is the point I am trying to say. So, in hard clustering, you have to mark each points belonging to a particular clusters only, remember this. On the soft clustering, you do not need to have this condition. Instead of assigning each points into a separate clusters, you can find out probability or likelihood of that point being part of a cluster. You do not have to assign it completely, you simply find probability of the likelihood. Let us say there are 4 data points and we have to cluster into 2 clusters. So, we can always evaluate the probability of each of the data points to be belong to a particular cluster. So, a data point can have a belongingness to cluster number 1, the probability of 0.8 and belongingness to the cluster 2 with the probability of 0.2. That is always possible, right. And this probability has to be calculated for all of these. So, that means what? We can actually handle the clustering in a very generic manner in case of soft clustering. Hard clustering is very clear, you have only one possibility. Well, what is the concept? Well, problem is very simple. You have a collection of unclassified objects, you have to find a means of measuring the similarity of the objects, right. So, if I go back to the board, I can explain it in a much better way. So, what is that? Okay, let me just erase this part. Let us say I have points like this. So, I must have a means, right. So, putting these points into one cluster. So, what I can do? I can simply find mean of these points in the cluster. These are my mean. You may say, sir, how do you find the mean? Very simple. You know y, you know x, forget about x and y. You know the data points, right? It can be anything. Okay. So, let us put y. I do not want to put y because you will get confused otherwise, because this is not this unsupervised learning. So, you have only x. Okay. So, now you know that. So, you know for each point what are the x values. So, distances basically this is 0. So, then you can calculate the mean of that, find the mean and place it here, right. So, then what happened? We have done the same thing for each of these seemingly 1 clusters, but they may not be, right. So, then you find out the distance of these objects, these points with this mean, correct. You can do that. This distance can be calculated as Euclidean distance or Manhattan distance or many other type of distances, and then find out how much distance you can allow, right. Am I clear? That is what it is, the idea is. So, means of measuring a similarity object is basically a distance matrix. Finally, you find the classes or clusters of objects with some standard quality is met, like maximize the similarity of object in the same class. What does that mean? That means you are determining the distance of each of the points from the mean. First, you define how much distance you can allow for a particular point to be belonging to that clusters. That means what? That means this distances, I have drawn so many distances here, 1, 2, 3, 4, right, 5 distances. So, I have to tell that if I can allow all of them as a part of these clusters. That means, what is the maximum distance I can allow from this center for each of the data point to be part of this cluster. If I say no, this is not allowed, this much is allowed, so this point is not part of this cluster. Okay, this point, okay, you can see that. I can always tell that. So that matrix is what is you have to define. That will determine the similarity. Okay. Essentially, this is an approach to discover some kind of a useful summary of the data, right? That is what is done. Ideally, we would like to represent the clusters and the semantic explanations. Okay. We would like to define clusters extensively or like general rule based or intentionally, right, or enumeration number based. Okay. So, you can always define certain set of rules, or you can always define some numbers to be part of the each point part of the clusters. Okay. So, best is obviously centroid approach, like the way I done. We get centroids, a central point of each of the clusters, assign point to the cluster of the nearest centroids, right. So, these are centroids. Let me just draw this one very clearly. This is centroid, okay. This is what is center. So, we are determining the distances like this, correct. So, you can clearly see this distance is this one is much larger than all of them. So, it is better to cluster these 5 points than this point. So, that is how actually it is done. This is one of the way, that is called centroid models, which we will discuss today. Second one is a hierarchical model. We can begin assuming that each point is a cluster by itself in a hierarchical model, and we repeatedly merge the nearby clusters. This is some measure of distance also already, or how good a cluster resulting group would be, average distance of the points of the cluster, etc. Some kind of a means of distance only. So, begin with each data point is a cluster itself. We do not define any center. We define each point as a cluster itself and repeatedly merge the nearby clusters, okay, by certain means of measure of distance. So, let us stop here and we will come back and discuss about this centroid approach today in terms of k-means clusters and tell you how it can be built on.